Go ahead, Peter.
Right, welcome back. And in this session, we're trying to show you what pose estimation is and how it can be used to extract gesture features from video data. Now, put very simply, pose estimation is a computer vision methodology that tries to determine the position and orientation of people in an image with the help of machine learning. That's what it does. It typically involves finding key points, typically those are joints, as we saw, of the people depicted. Now, an important thing to note about pose estimation is that it was not created for gesture people at all. We're just hijacking it. It has other applications, for instance, in medicine, movement patterns of in sports and things like that. It also can be used like some people use it in crime detection of surveillance cameras, whatever. The whole point is always the same. It basically to abstract over body positions. Now, the software that we're using in MULTIDATA, we're using two types of software because we are actually joining multiple teams here, as you heard. So the Erlangen and Murcia team traditionally have always worked with OpenPose because at the time we started this, MediaPipe wasn't at a state yet where it could use multiple people in the same frame. Whereas the MPI team has actually been using MediaPipe very successfully, and we'll see some of that later on. Now, in the first part of the talk, I'm going to talk about OpenPose, which is the older system. It says here 2021, but that's only when they managed to get their paper published. Actually, we've been using it since 2018. So what it does is it tries to assign body key points, pose key points to these joints. So this is the model that we're using for OpenPose. It's called the Body 25 model, and it assigns like all these numbers just to these joints, and then it does the same for face. So you see detailed face annotation with mouth and eyes in some more detail, and it does it for the left hand and the right hand, again with more details. So basically, you take an image and you give it to the computer, and the computer then assigns this. That's really what it does. It guesses where these points belong. And of course, it actually throws away this image because the image is a lot of information to process, and it keeps this skeleton here, which is much less information to process. Now, this is a visualization of the skeleton for the benefit of the humans. This is actually not what we typically store for the analysis. Now, if you switch on the hand and the face key points, it then looks like this. And with these data points, you can then try to extract data, as we will see in a minute. Now, the actual representation of the data looks like that. This is one of these dreaded JSON files that Raul said he doesn't want to scare you with. I just thought I'll show you very, very briefly that you see here pose key points 2D and then a bunch of numbers. Now, Yassine Yabdunan has created some slides that I'm stealing shamelessly here that show what this translates to. So if you have a video like this and it's annotated with OpenPose, then you'll see later on, this is Yassine's favorite gesture, or one of his favorite gestures. You basically have a coordinate system. And that coordinate system depends on the resolution of the video. So it's the number of pixels in each direction. Now you see here that unfortunately this goes downwards for x coordinates. That's computer vision people. We've flipped it for normal people. And then it looks like this. And the coordinates that we saw earlier, the numbers, is basically so we have OpenPose detecting people. So here it detected 3 people on that frame. This person, this person, this person. The last one of these actually, the second one of these actually has these pose key points that we're interested in. So we are seeing 0, 1, and 2, and that is actually the first key point. That's this one here, the nose. And the nose is then located 520 to the right and 180 to the top. And the next value here gives you a confidence between 0 and 1. That tells you how certain the computer is actually that it found a nose in this place. And then the same for the next one. You see for the neck key point, it's not as sure because it doesn't see the neck as well. It just sees a tie. And then for number 2, which is the shoulder, which is the right shoulder, it needs to guess it because it's hidden. We have occlusion because the hand is actually in front of it. So it's not as sure at all, but still sure enough. Okay, as I said, all this depends on what the video looks like because media recordings, and again, this is a slight difference in culture between the teams from Murcia and FAU. We are mainly working with media recordings, and the team at MPI who are mainly working with lab recordings. So we're going to see some differences on how these things are used. So for media recordings, we have huge variance in video resolution and thus the coordinates. Person size on screen, you saw Donald Trump in the top left corner, very tiny. People of different physical sizes. I mean, that is something that you have everywhere in lab recordings too. And so to be able to systematically compare these, we need to normalize key point coordinates because otherwise, I mean, how are you comparing 200 to 300 if the person is sitting somewhere else? So the solution to this is basically say we have a small person and we have a large person or image of that person. We just standardize. And to do that, in the data that we're using here in this demo now in the first part, we're actually standardizing on the distance from the neck key point at the chest, on the chest here, and the left shoulder. So that is number 1, and that is 0, that is 1. And then the distance here, that is our unit. So all distances we're going to measure in these units, because then we can compare it. Alaya?
No, sorry, I was...
Oh, it's just stretching. Okay. Yeah, so in this case, the important thing for the hand gesture is that he's pointing it somewhere and that he's not raising his entire hand, as we know. Then, yeah, the distance is between here and there, and of course it depends on the camera angle nonetheless. So if you're basically standing like this, you're normalizing different than this. And there is no full solution. This is where the caveats come in now, because there's multiple ways to normalize, and we'll see some others later. MPI are using it different for their lab recordings because they actually can see more of the person than we can in the media recordings typically. Typically, those media recordings are cut off somewhere on the torso, and therefore they can do something else. All of these have advantages and disadvantages, both the horizontal and the vertical ones. The vertical and the horizontal ones. Get my gestures aligned. And all of them are sensitive to changes in camera perspective, changes of speaker position, changes of speaker orientation. That is a bit of a mess sometimes. And that is something we have to be aware of when we use, particularly when we use media recordings. Sometimes you just have to throw away a lot because it's not comparable anymore. So also, very important warning for those who are now starting to say, I can compute averages. Always double check before publishing something, because there's crazy reasons why you get certain numbers sometimes. Not least because there's a certain commercial where one thing is repeated all the time or something like that. So really be careful. Now, the size normalization, MPI style, then it looks something like that. So this is shamelessly copied from Monica Kanakanti's slides. And you see here that these people are here made, basically zoomed in to always be the same size. So here they should always be the same size. Here they are not. So this is from 2 different videos. For some reason, it's the cheeseburger video and the life cycles video. Don't ask me. More details, I think, later. Here we see that then you can also normalize position by basically fixing that neck key point. And then if you're running that, now you can actually start comparing the hand movements, right? Before that, comparisons wouldn't have made much sense. But now we're in a position to say, okay, roughly if one person does this and the other person does this, it's roughly in the same place. So we get a better understanding of this. And how to use this fruitfully, you can see in the session after the coffee break when Monica is going to illustrate that more. Okay, but now back to practice. And that is, we're going to the multi-data pipeline. You've already clicked on how to use it. And well, you've already found the upload zip button. And so if you want, you can upload something yourself now. But I will just walk through this and show you what I've been doing, because actually processing would take very long for you. So we can't wait for yours to finish if we want to get that workshop finished. So again, we need to set a name. We need to type in what we want. So here we want the DF maker, data frame maker. We'll explain that in a minute. And the video key point detection. We have to select our file. We click submit and upload. And then, yes, I get an error message that the name of the file shouldn't be the way I made it. So, okay, we get a new one. Submit again. And then it means waiting. So we're here in the queued situation. And then once you've waited enough, you're in that position where one of them is processed, and you can hit download and get the file. Now these files are look as follows. So the file was called low bar. So imagine our study here is we want to compare gestures for high bar and low bar. Do people actually have different height of gestures? Now, this is a ridiculous question in a way. We assume that's probably the case. But nonetheless, it actually turns out quite a few of the low bar people and the high bar people have roughly the same level if you compare them. Because limitations probably of where you can gesture. I've selected a video here. You'll see that in a minute. That actually is pretty low for the low bar. So we have the low bar version 3. There's nothing in not processed, and here we have the process directory, and then this is the file names that we get out of the Newscape dataset, out of Red Hen data. So you'll learn more about that later. And then we have a DF maker folder, and we have a pose estimation folder in there, open pose, and then the key points. Those are these dreaded JSON files. You probably don't want to use them if you're not a programmer. And this is the output video of the skeleton. So let me show you first what the video is like. I'll play it twice.
Happy was to win the Pulitzer. That was a very low bar.
See, it's not hard.
Yeah, it's a really good career trajectory.
Okay, I'll play again.
Happy was to win the Pulitzer. That was a very low bar.
See, it's not hard.
Yeah, it's a really good career trajectory.
Right, and so with open pose annotation, it looks like this. And I'll walk you through some of the issues that we actually see there and that will make your life annoying if you work with media data and not lab data. Let's start here. This is from the very beginning. We see that the wrist is estimated to be here. Now, yeah, it can't estimate pretty much outside of its own point of view, viewpoint, but this is actually not the right position for the wrist, actually. So this is slightly off. It's also not easy to estimate it here, but sometimes the computer gets it, so it actually doesn't estimate a wrist because it's not visible. So we have that at the beginning, then it suddenly loses it, which is actually better in this case. Then we see once we move the hand gets moved up in the preparation phase, we see that, okay, wrist is there and fingers are there, but then in the stroke phase, the hand becomes too fast. And in media recordings, typically this means we have motion blur. Now, if you have control over your own lab, there is a bunch of video settings that you can set to make it better processable with OpenPose or any of these pose estimation tools. Talk to Sho Akamine here at the Max Planck Institute or Jeroen from the technical group. They have set this up to perfection now, I think, and now you get better results. With media, you have the problem here. You see we're losing the fingers, but what we're getting here is the wrist still. So the wrist is much more stable. And once we get into the end position, when it gets slower, again, the fingers are there, wrist is always there. That is why for many of these more simple research questions, you would rely on the wrist. So for large movements, you would not try to get the fingers because too often they are missing. Yeah?
Based on whether the fingers or the wrist are present or not? Is that based on the confidence values from the model?
Yes, so at the moment, the confidence values might get too low for us to visualize it. So here, if I recall it correctly, anything about 0.05 is visualized for fingers and face. Anything above 0.2 is visualized for body key point. but it's also then sometimes really missing from the data, or it's so low that we can't say this makes sense, and we delete it, right? Because I mean, I don't know. Honestly, I can't put fingers on this. Like, how should the computer do it? If really, I mean, there's a lot of interpretation if you actually draw fingers on this going on, which is because you, as a researcher, know where they were before and where they end up later. So, of course, you can make an educated guess of where they are now. But since these programs work on individual images and not on continuous video, they process each image separately. They don't make these assumptions. All right, and now we have this video and we've just looked at it. Now, we could have looked at it without the OpenPose and it would have been faster probably. So in order to actually benefit from this, you need to have numbers that you can run. And how to actually process these numbers, that is where Brian Hereño, the data scientist from the Murcia team, is going to introduce DF Maker, the tool that takes OpenPose videos or the output of OpenPose JSONs and makes nice usable data frames in R out of it.
Hello, I'm Brian. Thanks, first of all, for the invitation. I'm a little nervous, and for me, it's really hard to explain this in a way not to be so boring with a lot of data matrix and a lot of kind of mathematical stuff.
Right.
Sorry. I'm also. Okay. Then the thing is, we designed DF Maker just to make easier the way as we understand the OpenPose key points. We see here we have the connections. I mean, we have the type of the point. And we can see here 1, 5. As Peter said before, we can measure this as 1. And all the points we can connect it to create more complex figures of the pose and the body language. Then this is already in CRAN, in R. If you don't know, it's basically a big global repository about R code. And you just can download from your own computer, just writing install package, it's not there, but library, and then you just can execute over your folders. As Peter showed, that data, that JSON files, you can just download on it. Then what you are going to see on your data, which actually is in Parquet, is not in, is you need to open, you'll see later also. But what you are going to see in your data is first the X, Y positions of the OpenPose, then with a confidence value. This is quite important because then you can remove all the bad measures in so easy. Then you have the normalization position related to the chest. As you say, this is the origin coordinate, the chest, and then with the left shoulder we have 1, and then with that we can create the symmetry of the body. Then also the type of the point, because you also are going to find the pose about the whole body, the face points, left and right hands. Then you have the point. I mean, it's the number. It says a number about the point. And the frame, because you can use it through different movement. It's just not for a picture. It's for the video. It's for the video. Sorry. And then you have identifier if you mix a lot of videos. And finally, you have the people ID if you are using a multiply person study. But be careful with that, especially when the TV data, because sometimes OpenPose mix the speakers and the listeners, and then it's on research. Okay, what you are going to see is this kind of data sets. Basically, this is the origin coordinate. I would say is the chest. This is the right shoulder, and this is the left shoulder. I mean, I like it so much. It's number, but I like when you have 1 on one shoulder and -1 in the other, because this means symmetry of the human body, which is going to help really us to make to read the data and to create models, as we see here. This is the 5 point, this is 1, 0, this is the point 1, which is 0, 0, and this 2 is the -1, which is the right shoulder. All right, just to go fast, because probably I hope you can use this in your data, but it's going to be really under a lot of things. Then here we can see the original data for a small clip from OpenPose. And then here, what we see is how the coordinates are transformed. We cannot see really well here, sorry, but what we see, these numbers are not random, but is on the perception of the camera. While here, what we are seeing is the relation between the body. That's the main change. I mean, this is the 0, then this position of the wrist is related, this number, to the chest, to the own chest of the person detected. Here, this point is related to the camera, to where the video has recorded. Then when we see here the hand is going up, so in a moment, or okay, it's going to finish. This is the frames. All right, now it's starting. It's going to the, you see. Here we have this position is related to her chest, not to the camera position. That's the main change, because what we want to know is how the body is moving related to itself, not to the position of the camera. Well, that's what's offered DF Maker, this kind of data set that you can use for modeling, for big pylons, or for what you want. Yeah.
Can you, in principle, kind of modulate it to have, let's say, a position of hands not with relation to chest, but for instance, something they are pointing to?
Yeah. In our
Something outside the body.
yeah, you need to go to R, but it's possible. Okay, in the documentation of R, it is explained.
No, but if it's outside the body.
Outside the body. No, I would say outside the chest. You mean the chest?
No. Let's say they are like in an experiment. They would be sitting by a table, two people, and pointing things on the table to each other. So I would be interested in the position of the hand to the objects that they are pointing to, and not to the chest.
No, because you need then to detect the object. Here we are detecting just the body parts. Then, but if you have the detection of your object, maybe it can be built, but no. Here
So
is
it couldn't be added as a coordinate somehow there?
Well, it can be, but not within the platform. So this is like standard use cases. We see people communicating, but technically, what you're asking is not impossible, but it's something that we don't offer, and also we're not planning to offer, because it's beyond the scope of the kind of communication that we're representing here. But it's, in principle, either you have an object detection, or you actually give the coordinates of the object, and then depending on your camera perspective, you can like show where the fingertip is closest to. So that is technically possible, but not off the shelf at all. You need to have basically a programmer implement this.
Since I'm already talking, can I follow up? Because I noticed that actually the face here looks female. Like, is it, like, does it recognize the gender of the agent, or is it just like, it just drew this face so closely that it resembles the one of the...
It's only positions. I mean, it's related on her body. I mean, it's just the distance from her chest to her shoulder. Then what we see is the...
I'm talking more like of a face, the eyes and the facial features. So like if... Yeah, okay, but I didn't see the actor. I didn't look at all. I just looked at this and I thought, oh, it's a woman. Yeah.
Yeah, so it doesn't do anything of that. It tries to accurately render the position of these joints.
Yeah, basically...
If there's a difference between men and women in that respect, you will see it also in the rendering. But that's it.
Yeah, and it's just this point is what you see here. It's just not... It's previous interpretation. It's just to give the researchers the way to interpret your own data, but it's just the raw data, not without interpretation.
Yes, thanks.
Yeah.
I'm sorry if this is a novice question, but I'm having difficulty understanding the difference between what you mean by the camera perspective and then with reference to the person themselves.
Yeah. Can I hold the...
Yeah.
Sorry. Take this one. Thanks. I mean, okay, I'm really bad selecting examples. Sorry, but sorry, I'm also speaking. I'm not. But here you see these numbers. It depends on the camera. It's a pixel. This is just not a pixel. This is just inner body relationship
Okay,
between
thank you.
all the whole body. Then we can see, for example, the relation of the move of the elbow with the wrist. It's just we still don't have no idea. We are trying some models, but it's open for everyone to try your own models in multimodal communication.
So very simply put, if I now change the camera shot and, you know, I go back and I'm further away, everything is going to change here, nothing is
Nothing will
going to
change
change
there.
here.
Got it. Thank you.
It just, I'm gonna go, but it's just, this has no, it's just a pixel on the camera. It's just you are analyzing picture, but we are here analyzing the body, in the body language movement or communication.
The proportions.
The proportion, yeah.
There's two more questions here.
Thanks. When you are interested in eyebrows movements, what is the reference point? Because the reference point here is the chest, right?
Yeah, it's the chest. Then you're going to have this related to the chest. Why we have chosen the chest is because the chest and the shoulder is quite stable, because this is just like a line. But the problem, for example, we use the face and then you move. It can change the proportion between frames. But of course, you can use another one. You can define. But it's
okay.
not in. I mean, it's in the coding now, but it's not. That's in the multi-pilot, in the multi-data pilot. But of course, contact with us, and we can.
Well, first thing I'm saying, don't get your hopes up. Eyebrows are notoriously difficult because, particularly with open pose data, we've been trying a long time now, and we've tried all sorts of normalization strategies. So the problem is basically that the camera perspective is stable, but you're moving particularly the tilts, are the nods are the problem.
Is there a way of subtracting, for instance, the brows movement to the head movement?
Yeah, so that you can try that, and that's what we're doing. The problem is that the perspective changes when you nod your head. So what we're doing is we're relating the eyebrows to some points on the nose or some points in the eyes. But even then, when I look like this, suddenly the distance seen from that camera is very small. If I look like this, the distance gets much larger, and it looks like I'm raising my eyebrows. So we only can resolve this with 3D data, and there is something that we're trying actually at the moment with another tool, Sapiens by Facebook. Next year's next ISGS, I may be able to report what we found there. No, actually, we're trying to report this in September at a conference, but I don't think we have something that is like really reliable by then. We've been working on that for some time.
Oh, great.
Don't get your hopes up yet.
Thank you.
Melanie, you also wanted to ask something.
Very easy question. I just wanted to know what the units are for the normalized positions.
The unit is really
The shoulder is relative to the person.
so neck to shoulder.
Yeah, this is
That's one.
Yeah, you see here the one over up here, and the point is always there. Sorry. Sorry.
Doesn't matter which one.
Okay. Sorry.
She got it. Okay.
All right. Perfect. Yeah. That's
Okay.
okay. Thanks so much. And then Peter going on with the rest.
Right. So if you want to know more about DFMaker, you can look at the GitHub. You can look at Brian actually created in CRAN, the Comprehensive R Archive Network, or whatever it's called. He created a package in R that you can install directly out of RStudio, for instance. And for questions, as always, use our email address. Oh, and an article is forthcoming about the DFMaker tool. All right, so now we've got it in R. We can, of course, use R code to read it. Now, I know I'm going to put off a lot of you here because I hate R too. So I hate it with a vengeance. I'm a Python person. Yeah, I mean, what programming language? Don't get me started. Don't get me started. Doesn't matter. But we don't actually need to do much. So what we're going to do is we're going to use this library, which allows us to read the Perkit files that come out of DF Maker. It's called Arrow. I don't know why, but it's called that. So we load that, and then we just say, read this file. So this is for the video that we just saw, and give me a summary. And with that summary, I stop programming and go to ChatGPT, actually. So I tell it, this is the summary of a data frame in R. Paste. And then I get my instructions down here, which is I need a plot with ggplot2 that has time, as in the frame on the x-axis, plots the ny value, ny is normalized y, value for 4 and 7, that is right wrist and left wrist. For each person in frame, color codes the person ID, uses different symbols for points 4 and 7. Add a filter so that only those points where type point is where the type points is post key points, so I'm not interested in 4 and 7 from the face key points, I don't need those, are included. That's what I give it, and ask and there shall be given. ChatGPT gives me a complete program that I can use. The only thing that I added here is actually some comments for you. So this is already on the Multidata Google Drive. If you looked there yesterday when you got the message, all materials are online, no, it wasn't there. It's there now. But, okay, so it's there now. The one thing I changed is in that video towards the end, you saw that 2 people were suddenly visible. So at the beginning, he says it's like, that's a low bar. And then his interlocutor comes into view as well. We ignore that part. So cut off at 120 frames because then it gets slightly messier. Okay, so once we do that, it will plot you this. And what you see is basically here at the beginning, it found the wrist. Then we have this thing where it was too low, it didn't actually find it. And then we see it moved up here. And then with that data, you can do whatever you're doing statistics-wise. Like you can say, I want to know the highest point in that 2-second period. Or I want to know the average height of that in the 2-second period. Or something like that. That is your research then on what you can do with these numbers. Now, we're going to have Excel like CSV export. At the moment, we're only exporting Parquet, but I know that many people are more comfortable like with a spreadsheet than with R. If that's the case for you, well, ChatGPT to the rescue. I asked it, can you export that same thing in an Excel file, and it did. So, well, it wrote a script that does the job, and then you get the same thing here in Excel. This is the frame, and this is the key point number 7, normalized. Now, why only number 7? I also asked for number 4. Well, in that entire video, the right hand is not detected in that scene because it's too low. So it was never there. That's why. Normally, it actually prints both of them.
I just want to check that I'm understanding this. So what we're seeing here is the trajectory over time of
Yes.
one particular body part.
So this is frame, so 0.33 seconds, 0.3 seconds roughly. So, and we see that there is some sort of pause where we didn't detect anything. And then, yeah, and it's only the wrist. So this is the trajectory of the wrist over time for this short sequence.
So you could use these numbers as the dependent variable in a GAM if you had some idea about what the predictors might be.
Exactly, that would be the idea, that you basically say here the predictor is, very simply, is the corresponding word that's being uttered, high bar or low bar, and then you take the, say, as I said, the average, the highest point, or something like that as your dependent variable, or if you want the entire trajectory, I'm not good with GAMs, so I let you do that, and, but, yeah.
So for that, could I come back to a question that someone asked before, which was when you were asking about how, thank you. Someone was asking earlier about how to align words with, I can't remember what it was aligning with at the time.
With the audio at the time, yeah, audio features.
Yeah, but so what you'd need to do here then is somehow align this output with the transcription, for example.
Now, these come out of Newscape, so I can tell you that basically what this has, these video snippets are 4 seconds long, or 2 seconds, I don't remember, Raoul.
It's
4 seconds. So it's 2 seconds. So it's 2 seconds before before the person says low bar, and 2 seconds after the person says low bar. So you can actually say then, I mean, we know that gestures often come before the actual target, so you can say we start 500 milliseconds before the start of the word low, and we go till the end of bar, and that is the kind of section that we're going to look at for all of these videos.
But you can only sample at these roughly 30 millisecond
Yes,
time points.
that is how many, we have 29.97
Yeah.
frames per second.
What you're asking,
The video format doesn't give you more.
the complete alignment of everything, which is what you, that is something we do in our research, but still.
But still, you can't sample more than 30 frames per second on a video because that's all this is, so 30 milliseconds is the lowest lowest
Yeah,
unit.
that's understood, but then the issue is how you align the speech with it, I guess. But maybe you can you then sample the speech every 29.7 milliseconds or whatever it is?
Yeah, I mean, you basically, that is your algorithm, for you to decide.
Yeah.
At the moment, you see in the transcript, we have a start and an end time. And these ones here can be translated into start and end times basically by saying 0 to 0.033, 0 to 0.066, and so on. We'll see that actually in an example later on today.
Okay.
But,
Thank you.
but
Thank
the
you.
alignment
Yeah.
always goes via the timecode,
Yeah.
always via the timing.
Yeah. Thank you.
All right, and that is where, yes, we need to hurry. How to actually, one of the issues that you see here is that we have these little spikes. So here suddenly for one frame it's further up, here for one frame it's further down. This would mean that somebody moved their hand 30 milliseconds in this direction, 30 milliseconds in that direction. That's physically impossible. What we see is actually noise. And this is something that we need to deal with if we work with these computer-generated data. And Ferdinand is going to tell us a bit more of how to do that.
Oh, thank you. Sorry, Hello, everyone. Welcome to my presentation. Does it work?
Say who you are.
Oh, sorry.
Sorry.
You're right. This is open in a second window. The MPI requires their own
Template. Yes. Okay. Welcome, everybody. I'm from the MPI team. Today, I want to talk a bit about how we get from video data to something which has kinematic value. So some kind of small analysis already. My presentation is like about two phases. One about the tool we're using, which is MediaPipe in that case, and the second phase is about what kind of techniques we're using to like smoothing and normalization in our pipeline we provided to the MULTIDATA platform to get better results for kinematic measures. I'll briefly go over MediaPipe. Basically, everything what Peter said in the beginning with the nice rainbow skeleton and the key points is the same for MediaPipe. Another thing which makes MediaPipe in some cases more powerful is that it introduces a set axis. So another axis, which of course is hard to estimate only by video data because the camera has to estimate that depth of the set axis. But also maybe to make Peter happy, this is in Python, maybe for all the R haters out there. Nice. So what it's actually doing, it puts a key point on every joint we have, and for the hand, for the body. Exactly. This was everything with MediaPipe. Now I'll go into the scripts we provide to the MULTIDATA platform. The first one basically takes video input and turns it in a CSV file. And I'm showing you what we already can do with this CSV file. And the second one takes that CSV file, applies some techniques I will go into more detail later, and gives us a heat map. And to maybe let you peek a bit under, how do you say it in English? To not make this look magic in the MULTIDATA platform, because in the MULTIDATA platform, this is only click and apply, right? I want to show you this is like based on computation. Okay, let's start with the first script. We have a video input. Of course, with every kind of video input, it would be nice to have good lighting, have as much of the body in the video frame. So for the x-axis of MediaPipe, it has an easier time to estimate it, the more key points it has from the body, basically. Exactly. Then we get these key points. We talked so much already today from a different tool though, but basically work the same way. We take them and we put them in a CSV file. That is a bit different to what OpenPose does because we now get just the time on one column and then the confidence, how confident MediaPipe is that this key point is actually there where it thinks it is, and then 3 columns for Z, Y, and X axes. Exactly. So this looks like this. For 2 key points, you have the, wait, I think I have a laser pointer, yes. You have the time here and the Y-axis of the wrist, of the left wrist, and the Y-axis of the right wrist, and displayed in the CSV file. This is already in Excel, so you can really take this file, put it in Excel, and get already your first kind of kinematic features because the Y-axis represents the height of the joint basically, and then we can average it out, create a box plot, get some kind of intuition. Okay, over the span of this video, the average or median height of left wrist is XY compared to the right wrist. Yes. Anything clear? Okay. Please interrupt me if something is not clear. Yeah.
Brief question. In your spreadsheet, I noticed that these were all still quite small numbers, right? Between 0 and 1
Yes.
range. Are these normalized to something? And if so, what?
The way thanks for the question. I can go in a bit more detail. OpenPose works from -1 to 1. Pixel coordinates, exactly. And MediaPipe, instead of using pixel coordinates, it uses a -1 to 1 frame in both directions. That's why the values are quite small. That's why you always will find numbers between -1 and 1.
Why is the time every third jumping to positions after?
Sorry, what was that?
Like the time.
The time.
Yeah.
Yeah.
Like,
this is a millisecond. So.
yeah, I know. Yeah, so it's 133 then 166 point.
Oh,
and
this
then
is just the way Excel displays it in that setting I used. This is nothing special about the way we save the data or anything. Yeah. Cool. Okay, that was that was basically everything about the first script. Yeah, basically everything was said. Basic things about video. Make sure that you have high contrast will improve your quality of your kinematic output. To the next script. The next script takes already this CSV file we just talked about. Applies smoothing, no worries. I'll talk about it a bit later, what exactly smoothing, because there's a lot of different ways of smoothing data. Applies normalization, same thing here. I will talk about it a bit later. And creates a kinematic heat map where we can already get some insights. Yes, why do we need smoothing? So our key points, how do I start this? I hope this works. Oh yeah, is it running? Oh yeah. Our key points we get in this beautiful CSV file don't always represent the real world. As we can see here, a lot of jitter in the hips. This is not the actual movement of the person. So with smoothing, we try to get rid of as much of this jitter motion and keep as much as the actual movement of the person. How this works? Yes, this is just, we want to get rid of noise because of a lot of things like motion trajectory calculation, kinematic measurements. Noise just makes our analysis a bit worse. How this works, there are a lot of different things. This is really signal processing at that point, but basically we look at a couple of frames and either average or think about how we can get rid of these high peaks in the movement we just saw with the hips before. Exactly. There are like a lot of different ways. Yeah. This is in a bit more detail. This would be the left index finger on the Z-axis over time. So the time axis would be the x-axis in that plot, and the position would be the y-axis. And what we can see, the black plot represents the raw data, so the unsmoothed data. And this is playing, yes. And the green plot shows the smoothed out data, so where we get rid of all these noise. Of course, there's a pitfall to smoothing, to every kind of signal processing you apply. There is the pitfall of either over-smoothing, so your movements get really delayed or over-smoothed, or under-smoothing, so you still have a lot of noise in the data. Yes. That was the smoothing part. Now we also want to normalize. Very, very similar to what Peter was saying. Because we want to compare kinematic measurements to each other, or like to multiple people, we have to normalize on something. There are a lot of things you can normalize on. You can normalize with respect to size, with respect to position, with respect to camera point, what we had before. A lot of different ways to normalize. What we want to normalize is on the size of the person, but also because the heat map is a two-dimensional output, and we're working with three-dimensional data, we want to map this three-dimensional data on a two-dimensional plane. So what we are basically doing, don't look at the code, it's not that important, just stick with me. What we are basically doing is we take the midpoint of the shoulder. So two things we're doing here. First, we want to calculate the plane we want to map our heat map on. This is where we take the shoulder axis and the torso axis to map it on. So we have a two-dimensional output. Even if I gesture like this, and then I turn and I gesture like this, I want to display this in a 2D way. And the second thing is we want to normalize on the size. So how do we do that? We look at the midpoint of the shoulders, a bit different to open pose. MediaPipe doesn't give us this point because it's not a joint we're that much interested in from a MediaPipe perspective, not from a gesture perspective. We take that point, we take the midpoint of the hips, normalize on the theta, on that length, and make it a standard size. Yes. Lot of code. Scale factor. Yeah, this is basically we put all of the participants on the same size of this distance, so we can compare them more easily. And yeah. So why we want to normalize? Again, we want to cross subject analysis, and of course choose techniques based on your research question. I don't think I have to say that here, but yeah, and then we can get output like this. For example, these are heat maps that represent time spent in certain locations. Monica will go in more detail when it comes to heat maps. Any questions?
Is it possible to normalize time? Because when you are analyzing several videos from the same participant, for instance, but the duration of each video is different from each other. So is it possible to get a heat map of everything, of all productions for a single speaker? But in that case, we need to normalize time because the utterances, the productions have different lengths.
So am I understanding that correctly? Maybe Monica wants to say something.
When you mean by normalizing with time, I'm assuming it is with the gesture rate or the signing rate. Is that?
No, it's about it's basically about sample size. So you have people who are talking for half an hour and you have people who are talking for 15 minutes, and then you want to compare the heat maps. Of course, there's going to be more time spent anywhere for the 30 person than for the 15-minute person. That's the problem that you're facing there. And at the moment, we don't account for that. So every dot is just time spent. But in principle, you can actually adjust the opacity of these dots and the way they multiply. But that is, you're on your own for this again. That is something that you can take the R code and, or whatever, and modify it.
So you are not planning to have this kind of normalization?
I wasn't, at least.
Let's get together and write a grant if you're really interested.
That's basically,
So guys, remember.
yeah, that's basically the answer that you can get to for most of these things, of course, yeah. If you can get money for paying somebody to do that, then somebody will do it. Otherwise, they will do what they currently want to do in their own research, and then that is what we're offering here.
Yeah. Thank you.
Okay. Oh, sorry.
This is just a question of clarification. On the CSV file that you showed us,
Yes.
yeah, back a bit.
Yes.
There, yes. It only shows the y coordinates, but
Yeah.
you do also have the x coordinates.
All of the
do you?
coordinates, X
Ah,
and Z2. This was just for
okay.
showing it here. Yeah.
Thank you. Thank you.
Okay. I hope I could take away a bit of the magic.
I'll have one more slide for summary,
And then you
and then we're... Sorry, this is not the one, so Ferdinand's presentation. So, to conclude, very simply, pose estimation, as we've shown today, forms the basis of the multi-data pipeline's tools for gesture annotation. So we're stealing that from the computer vision people, and appropriating that in some way. The raw data is often too messy to work with, so filtering, normalization, smoothing, and so on can help. And with a basic understanding of these tools and data structures, we can actually extract meaningful results. And that is basically the cliffhanger, because that is what Monica and Yassine and Armin are going to show you after the coffee break. See you then.
10 to 4.